Welcome back to Relativity 103, Galilean Relativity. In this video, we're going to move on to the Galilean transform, which is how we change our basis in space-time diagrams for Galilean relativity. We've seen that in Galilean relativity, observers in different reference frames will agree on time, but they will disagree on position. For example, if we look at this green event point on the space-time diagram, according to Einstein's reference frame, this will happen 2 time units into the future and 1 space unit to the right, compared to the origin. From the plane's point of view, the green event point is 2 time units into the future and 9 space units to the right. From the car's point of view, it happens 2 time units into the future and 0 space units away. This is because the event happens to be right on top of the car's world line, so the position of the event is equal to the car's position when it happens. So we can measure the time and space coordinates manually by looking at the space-time diagram, but it would be nice if there was an equation that could do the coordinate conversions for us. So let's try to find equations for the car's time and position components, calculated from Einstein's time and position components. We know that in Galilean relativity, time is universal, and so the time for the car is equal to the time for the scientist Einstein. And I'm going to refer to Einstein as man in the variable subscript, just because it's a short word that's easy to write. But what about the position coordinates? We can start by noting that the speed of the car in Einstein's reference frame is 1/2 space units to the right for every time unit. At the origin, Einstein and the car are at the same position. After 1 time unit, their spatial separation is 1/2. After 2 time units, their separation is 1. After 3 time units, their separation is 1.5, and so on and so forth. The separation delta x between Einstein and the car is 1/2 multiplied by time, where 1/2 is just the speed of the car. So the car's position coordinate is equal to Einstein's position coordinate minus 1/2 times time. If you're wondering why I used a minus sign instead of a plus sign, just remember that the car's position according to Einstein is 1/2, 1, 1.5, 2, and so on. But the car's position according to itself is always 0. So we need to subtract off this separation in order to measure position from the car's perspective. Now, if I just wanted to teach you Galilean relativity, I could just tell you that this is the Galilean transform and say that's the end of it. However, I'm assuming that you want to learn general relativity in the long term, so we're going to need to study the Galilean transform more deeply. I want you to remember that basis vectors and vector components are 2 sides of the same coin. Anytime we're dealing with vectors, we need to think about both the basis vectors and the components. It doesn't make sense to talk about one without talking about the other. So the Galilean transform isn't just about changing components. That's only half the story. The Galilean transform changes both the basis vectors and the vector components, and they change in opposite ways. In Relativity 102, I showed that if we took the basis Ex and Ey and measured this pencil to have components 1, 1, if we doubled the length of the basis vectors, the components would become 1/2, 1/2. We saw that the basis vectors and vector components behaved in opposite ways. When the basis vectors grow, the components shrink. For this reason, we call basis vectors covariant, and we call vector components contravariant. Vector components do the contrary or opposite things that basis vectors do. I'd like to show you how the Galilean transform affects the basis vectors, which are covariant, as well as the vector components, which are contravariant. We learned in the last video that every inertial frame has its own space-time basis, where the time vector is angled to align with the frame's world line. We're going to find that knowing how to change from the scientist's space-time basis to the car's space-time basis will result in the coordinate change formulas that we need. So let's start with the scientist's space-time basis and see if we can convert it into the car's space-time basis. So we're going to try and build the car's basis vectors out of the scientist's basis vectors. So what would the car's time vector et tilde be equal to if we needed to build it out of et and ex? Well, it looks like we need one ET vector and 1/2 of an EX vector. So I'll write in the components 1 and 1/2. And what about the EX tilde vector? Well, it looks like EX tilde is exactly equal to EX. So we need 0 ET and 1 EX to build EX tilde. To make things simpler, I'm going to leave out the 1s in this formula and get rid of the term with the 0 in it. So we've successfully come up with the formulas that let us convert Einstein's spacetime basis into the Carr's spacetime basis. Now let's try and go in the other direction, where we use the Carr's spacetime basis to build up Einstein's spacetime basis. To build the ET vector, it looks like we need one ET tilde and 1/2 of EX tilde, but pointing in the opposite direction. So the components of ET in the Carr's basis are 1 and -1/2. And again, since EX is exactly equal to EX tilde, to build EX we need 0 ET tildes and exactly 1 EX tilde. And again, removing the 1s and getting rid of the 0 term, we get this. So we now have equations to switch back and forth between Einstein's basis and the Carr's basis. You'll notice that this first set of formulas has a positive 1/2 and the other set has a negative 1/2. This is because the equations are opposites of each other. If we start with Einstein's basis, then change to the Carr's basis, and then change back again, we should end up with what we started with. I'll show you what this means in terms of the math. We'll start with the equation for ET in terms of the Carr's spacetime basis. Then let's replace ET tilde and EX tilde with the formulas from this box. Notice that the positive 1/2 EX and the negative 1/2 EX cancel out, and we're left with ET equals ET. So applying the Carr to man equations and then applying the man to Carr equations brings us back to where we started, since the equations are opposites. Now let's go through a simple example for how to change spacetime components using these change of basis equations. So we know that the S vector is made up of 3 time vectors and 4 space vectors in Einstein's frame. Now let's use the change of basis equations to get the components for the Carr's reference frame. We can use substitution to replace ET and EX using these equations containing ET tilde and EX tilde. We can distribute the 3 here to get 3 ET and -1.5 EX. And if we add -1.5 and 4, we get 2.5. So we can see that the components of the vector in the frame of the car are 3 time units and 2.5 space units, which matches up with our spacetime diagram. So we successfully changed coordinates in one specific case here, but we should try and get formulas that work for all cases for any vector. The first thing I'll do is replace the velocity 1/2 for the car with a generic velocity v in these formulas. Let's start with a generic spacetime vector s equals TET plus XEX in Einstein's reference frame. Then we replace EX and ET using these change of basis equations. Then we distribute the t here to get TET tilde minus VTEX tilde. Then, since both of these are terms with the EX tilde basis vector, we can rewrite it as a single component, -VT plus X. Now, since this formula is written in terms of the Carr's spacetime basis, ET tilde and EX tilde, this means that the components are just equal to T tilde, the time according to the car, and X tilde, the position according to the car. So we now have equations for changing between the man's components and the car's components. T tilde equals T because time is universal, and position X tilde equals -VT plus X. Just like we saw before, we just take the man's position and subtract off the change in the car's position due to its velocity. We can also do the same thing in reverse, and start with a vector in the car's basis with components T tilde and X tilde, and then use these equations to replace the basis vectors et tilde and ex tilde. We distribute the t tilde, and since both of these terms contain ex, we can combine them and write the component vt tilde plus x tilde. But since this is written in terms of the Einstein spacetime basis, these components are just t and x. So we can write the equations t equals t tilde and x equals vt tilde plus x tilde. So we've discovered these four sets of formulas for changing between the basis vectors and the vector components for the man and the car. And the Galilean transform is really all of these formulas put together. Earlier I mentioned that the two formulas for the basis vectors are opposites, because there's a plus v here and a minus v here. That means that if we use one set of formulas and then the other, we end up back where we started. The formulas for changing components are also opposites. There's a minus v here and a plus v here. And you can check for yourself that if we use one set of formulas and then the other, we end up back where we started, with the original variables being equal to themselves. Now, what might be less obvious is why we have a plus v here for changing the basis from the man to the car, and we have a minus v here for changing the components from the man to the car. And the reason for this change in sign is covariance and contravariance. Remember that basis vectors are covariant and vector components are contravariant, which means they do the opposite thing that basis vectors do. What's happening is that the plus v term here is pushing the et tilde basis vector to lean more in the positive horizontal direction, and that's why it's slanted. Meanwhile, this minus v is pushing the x tilde component more in the negative direction. In Einstein's frame, the position component of this event is 2. But in the car's frame, the position component has been pulled toward the negative direction and is just 1. Because this event is closer to the car's world line compared to Einstein's world line, the position component for the car is smaller. So that's why the change of basis and the change of component formulas are opposites. The plus v here pushes the e tilde basis vector in the positive direction, and the minus v here pushes the x tilde component in the negative direction, the opposite direction. So the stuff I've explained in this video about opposite formulas and covariance and contravariance might seem hard to understand right now. But all of it becomes much easier to understand if we write these equations in matrix array notation. So let's try writing the change of basis equations from the man to the car in array notation. I've added the 1 and 0s back in so we can see exactly what all the components are. It turns out that to rewrite these equations in matrix notation, we write the row et tilde ex tilde equals the row et ex times this matrix, which is called a Galilean matrix. We can confirm that this is correct by doing the matrix multiplications and making sure we get these formulas when we're done. So when we do this row times this column, we just use the rules of first times first to get 1 et, and second times second to get vex. And since this is equal to the first element in this row, et tilde, we've confirmed this matches with this equation. Next, if we do this row times the second column, we do first times first to get 0 et, and second times second to get 1 ex. Since this is equal to the second entry of this row, ex tilde, we've confirmed that this matches this equation here. We can do the same thing for the formulas that change components from the man to the car. This time we get the column of vector components t tilde x tilde equals a Galilean matrix multiplied by the column tx. Notice that this Galilean matrix has a minus v because of the minus v in the original formulas. So we've written the equations in matrix form, but you might still be a little bit confused about why we write the basis vectors as rows and why we write the vector components as columns. and also why this Galilean matrix has a plus v, and why this Galilean matrix has a minus v. It turns out that these two Galilean matrices are inverses. When we multiply them, we get the identity matrix. Right? When we multiply this row by this column, we get 1 times 1 plus 0 times negative v, which is just 1. And you can check for yourself that if we multiply all the other rows and columns together, we just end up with the identity matrix. And this is why this is so important. If we start with the spacetime vector S, written in Einstein spaces as TET plus XEX, we can write this in array notation using a row of basis vectors times a column of vector components. Then we can insert an identity matrix in the middle here, since multiplying by the identity matrix doesn't change anything. It's a bit like multiplying by the number 1. But now we can split this identity matrix into two Galilean matrices that are inverses of each other, one with the positive v and one with the negative v. Since they're inverses, they multiply to give the identity matrix, and so we still haven't changed anything. And now we can see very clearly that the first Galilean matrix with the positive v is multiplying the vector basis, whereas the second Galilean matrix with the negative v is multiplying the column of components, and it's doing the opposite thing, or the contravariant thing, because it has this minus v here. And if we check our change of basis equations, we can see that this multiplication just gives us the cars spacetime basis written in a row, and this multiplication just gives us the cars components written in a column. So this shows that the vector S is invariant. We can write it in Einstein's basis or in the cars basis. Both formulas are equal to each other, just written using different points of view. The reason that they're both equal is because basis vectors are covariant and change using one Galilean matrix, and the vector components are contravariant and change with the inverse Galilean matrix. When the basis does one thing, the vector components do the other thing. The opposite changes balance out so that things are still equal. And we can also convert the other equations that change from the car to the man into array notation. The rows of basis vector transform with this Galilean matrix using the minus v, and the columns of vector components transform with this Galilean matrix with the positive v. So here we have all four formulas for the Galilean transform written in array notation. So let's sum up everything we've learned about the Galilean transform. We know that the change of basis equation and the change of component equation use opposite or inverse Galilean matrices because of covariance and contravariance. When basis vectors do one thing, the vector components do the opposite thing. That's why the v in the basis equation and the v in the component equation have opposite signs. This is what allows us to start with a vector written in one basis, insert an identity matrix, and then change the basis using one Galilean matrix, and change the components using the opposite Galilean matrix. The opposite changes, or opposite Galilean matrices, will balance out, allowing us to rewrite the vector in a different frame of reference. Also, the two change of basis equations also use inverse Galilean matrices, one with the positive v and one with the negative v. This is because if we use one and then the other, we end up back where we started. And remember, basis vectors are covariant, so we write them as rows and place them on the left of the Galilean matrix. The two change of component equations also use inverse Galilean matrices, for the same reason. If we use one and then the other, we should end up back where we started. And remember, vector components are contravariant, so we write them as columns and place them on the right of the Galilean matrix. So to understand the Galilean transform, just remember that the Galilean transform changes both the basis vectors and the vector components. And even though there are four formulas here, if we understand how the Galilean matrix changes one basis, We can automatically figure out the Galilean matrices for the other three formulas, just by knowing that we can invert the matrix by changing the sign of V. In the next video, I'll discuss the Euclidean metric tensor, which is a tool for measuring the lengths of vectors.